So the first concept I want to talk a little bit about is impulses. And you guys probably have seen these. Maybe you've seen these in differential equations, the delta function. At all? Have you guys seen that? All right. So in general, this notion of basically what I'm talking about, what is a signal? I use that term a lot. All right. So when I say a signal, like for instance, if you look at in project 1, right? Problem 2, for instance, I gave you, you're basically filtering an audio signal, right? That signal, basically, if you look at it, it's a voltage. All right. And so in reality, oftentimes we talk about real world information that can be modeled as a mathematical function, right? So if I actually have that audio waveform is basically a wave, and we model it as some kind of a mathematical function to be able to do analysis on it. So like when you do the high pass filter that you do in problem 2, right? You need some kind of a mathematical model to be able to properly design that filter. Now, I didn't have you guys design the filter in problem 2. I had you implement it. But there is some design. In other words, the RC value that's in that, there was design that has to go into those RC values, okay? So if I talk about, modeling this, if I say an A note, it's applied for only 2 seconds. All right. Anybody know what frequency an A note is? So it's 440 hertz. If I said I had a 440 hertz cosine wave, how do I write that? How do I write mathematically a 440 hertz cosine wave? Cosine of what? If it's 440 hertz. I'll sit here for all day. It's fine. Me. How do I write a cosine that's 440 hertz?
That would be 440 cosine.
No. Frequency never goes in the front. 2 pi 440, yeah. 2 pi 440 t with some amplitude, right? The amplitude controls how loud it is, right? That's what goes in the front. If I said I wanted to apply it for only 2 seconds, I'm not going to talk too much about this, but we know this function u of t. What's u of t do? It's a step function. So it's a function that at time t equal to 0 becomes 1 and stays there forever. What if I told you what would u of t minus 2 look like? If I have a u of t minus 2, what would u of t minus 2 look like? How can I check what that would be? Well, I can plug in what happens at t equal to 3 seconds, let's say. So u of 3 minus 2 would be u of 1. That would be equal to 1. If I plugged in u of 1 minus 2, that would be u of negative 1. So u of negative 1 is supposed to be 0. This guy is supposed to be 1. So what happens if I have t minus 2? It'll start at 2. It'll start at 2. I've got a shift. So one way I can write this is actually u of t minus u of t minus 2. Right? That would be one way. That would be something that lasts for 2 seconds. Now, this notion of shifts and things like that. So what is that? If I say u of t minus 2, is that a shift to the left or the shift to the right? That is a shift to, what is that? The right, right? So this would be u of t minus 2. Now, you guys should be pretty familiar with the notion of shifts and things like that. If I do a plus, then it becomes to the left, right? And if it's a minus, it's to the right. Okay. All right. So we have, and there's a number of pretty important waveforms. And the reason why we learn all the math basically is because we need to be able to model things that happen in the real world. So modeling signals, right, that exist, audio signals, power signals, whatever, right? So the tools that we have that are really powerful for us, we already said sine and cosine. And we're going to go back to that. And then we're going to lead into the next thing here, which is additive combinations of sine and cosine. So when I say an additive combination of sine and cosine, basically what I mean would be something like this. If I had a square wave, a clock signal, right? If I'm talking about a digital system, if I have a clock, that's a square wave. This guy is a combination of sines and cosines, right? So and that's what Fourier is, and that's what we're going to talk about more over the next couple of lectures. All right. This is a pretty powerful sort of thing. When I have periodic waveforms, we use them all the time. All right. We talk about power systems, controls, robotics. We use periodic waveforms all the time, and the math allows us to do some design with it. All right. Unit steps are useful when we're thinking about digital circuits. And then what I'm talking about today, impulses or Dirac deltas, all right, are also a pretty useful thing. Very simple concept. All right. Kind of a deep mathematical concept, but pretty simple to deal with. All right, so what is an impulse function? So basically what I think of is an impulse function, it models something that happens very rapidly in time, where I have a lot of force that's applied for a really short time. All right, so the example I give, right, is if I've got a situation where, let's say you're hitting a baseball, right? So what's happening in that short time is you're applying a force to that thing, right? The batter is applying a force to that thing, and it's not for very long. So if I thought of, like, mathematically, what is the force that's applied? Well, you would probably say it's a steady force that's applied for a little bit of time. I'll call it delta t, right? So a lot of force applied for a very short time. It's a very rapid change in energy because that pitch goes from 95 miles an hour one way to probably more than 100 miles the other direction very rapidly. So there's got to be a lot of force applied in a very short time for that to happen. So most likely the force value is really high and the time is really short, right? A very common thing that happens in the real world, right? In fact, this kind of thing happens. So in circuits one, you guys probably still haven't gotten to like capacitors and stuff yet if you're in that class, have you? No, okay. All right. So you wouldn't have a sense of this yet, perhaps, although you do maybe know you've dealt with inductors before, whether you realize that or not. If I take a hairdryer and plug it into the wall or a toaster or something like that, and I pull the plug out, what happens if you have a device that's drawing current that you pull out of the wall real fast? The spark, right? That spark is because there was a rapid change in the stored energy in that system. All right. And that happens, right? That basically there is some impulsive event that's kind of occurring. All right. So we often try to idealize that thing. So the example I give of the baseball player, he hits the ball, right? So a lot of force applied for a short time. We kind of idealize this and say, what happens if he's touching it for a really tiny short, infinitesimally small period of time, and let that delta t go all the way to 0. So we define this thing that we call the impulse function delta. So we use the Greek lowercase delta like that, right? We call it the Dirac delta function after the person that kind of derived it, all right? Or the impulse, all right? So it's an idealization of a signal that I described like this, like hitting the ball. That's very large near t equal to 0. So a lot of force applied to the ball. It's very small after that, right? And we say the area under it, the integral of it is 1, right? So like if you look at this example here, right? Here I have something that I'm saying is a time period epsilon wide. His height is 1 over epsilon. I gave you a rectangle like this that had a width of epsilon and a height of 1 over epsilon. What would be the area of this thing? Yeah, it would be 1 over epsilon times epsilon, or 1, right? So what we say here is I let epsilon go to 0. So if I let epsilon go to 0, if I let this guy get super skinny, what happens to the height of that thing? If the width epsilon gets super tiny, what happens to the height? The height's 1 over epsilon. If the width is 0, 1 over 0 would be what? Don't tell me undefined. It is undefined, sort of, but
We go to infinity.
it's approaching infinity, right? So we say infinity is undefined, but it becomes really, really big, right? Becomes very high. That's the way we think of this thing. But what we say is we define it like this. All right. So we think of delta t, we draw it as an arrow. And we define it like this. We basically say that the area under that curve, the area of this thing is equal to 0. So by definition, what I say is if I only have this impulse, delta t dt, from negative infinity to positive infinity, that area is equal to 1. All right. That's the definition of it. All right. And we draw it basically as a solid arrow like that. All right. So that right there is the delta function. All right. And that's there. In other words, it has no specific height. What we're saying with this thing is he has 0 width and a height that is undefined. It's approaching infinity. However, his area is 1. All right. So that's the basic idea of it. And models, essentially, what I'm saying is that any signal models something happens in the real world. It models an impulsive behavior, something that happens very quickly, very sharply, but very shortly, okay, in time. So I wrote this thing out here where I said, okay, I can say that as long as, so if I write this integral here, integral from A to B, that integral is equal to 1 as long as A is less than 0 and B is greater than 0. All right, so let's see what that means here. So I just said, so integral A to B of delta of t. This guy is very easy, and the integrals that I do with it tend to be really easy. Let's take a look at these two examples I have here. So A is here, some negative value. B is there at some positive value. And delta is right here. So this is the delta function right there. So for this top one, so for the top graph here, what would I say is the area between A and B using this definition? How much area is enclosed as I integrate from A to B? Well, the definition of the area under this thing is 1. Okay. For the bottom graph, what have I changed with the bottom graph? Well, bottom graph, A and B are here. Just looking at this, even if you didn't know anything about the delta function, right? What's the area enclosed as I move from A to B? 0, right? Because I didn't include that thing in the integrals. All right. So it's fairly straightforward. Basically, what I'm saying is the way this delta of t is thought of, right, is I think of it in terms of the area that's under it. So delta of t is equal to 0 for any value that's not equal to 0. Delta of 0 isn't really defined because the height is really high, right? And we kind of think of it in terms of the area under the curve. Okay. So again, this is pretty formally mathematical. All right. So we don't get too concerned about this, but let's look at this guy right here. So if I say the integral from A to B under this delta, this guy is, and we say it's ambiguous if A equals 0 or B equals 0. Why would I say it's ambiguous? If A equals 0, B equals 0. What do you think I mean when I say it's ambiguous? Well, it's kind of unclear whether or not you're actually including it, right? If this thing is located at t equals 0, and I start my integral at 0, or end my integral at 0, not really clear if I'm enclosing it or not. All right, so in order to kind of avoid confusion, sometimes we talk about limits like 0 plus, right, or 0 minus. So in this case, when I say 0 plus to 1, the plus usually means that it's a little bit after 0. That means the integral here would be 0. I wouldn't enclose this guy. I say 0 minus to 1, that would be a little bit to the left of 0. That would implode. Okay. And then there's some other examples of that. Chances are I'm probably not ever going to give you something like that you have to worry about. Okay. But nonetheless, it is important to understand that concept. I know in circuits, I often talk about the value on a capacitor at 0 minus and 0 plus, because I'm talking about at t equal to 0, if we close the switch at t equal to 0 or open a switch at t equal to 0, not really clear what's happening exactly at t equal to 0, right? Because that's the moment when the switch opens. So I talk about what happens right before and right after. So I use that 0 minus and 0 plus nomenclature a lot. All right. So one important thing about the derivative, or sorry, no, skipping ahead there. So one important thing about the impulse is it is related to the derivative at certain locations. So one thing that you guys learned in calculus, right, is if I gave you a step function, right? So if I gave you that guy right there, so you didn't call it a step function. Calculus, you would have said something that goes from 0 up to 1 real fast. So t equal to 0. What would you say is the derivative of this thing at t equal to 0? What would you say is the derivative? So if you were in calculus and you were asked to define the derivative at that point where there's a rapid change in the function, what would you say the derivative is there?
There's no derivative, is there?
There is. All right. You said it was undefined, but in the context of signals, we usually try to give ourselves some tools to be able to think about it. And so what we say is that it's actually the impulse function. All right, so let's think about intuitively what's going on. If I looked at a real system, this in no way on the earth that we all live on could I ever cause a signal to go from 0 to 1 in 0 time. It would never happen. Physically impossible. It might take a nanosecond, right? That's effectively almost 0. Right? It might take a picosecond. That's effectively almost 0, but it takes some time for a waveform to go from 0 volts to 1 volt. And we see this all the time. Like if I have a switch that closes, unless that switch can close in infinitesimally short time, which it never can, there has to be some rate of change. So if I look at this guy right here, right? Let's say it takes t seconds for this guy to go from 0 to 1. T could be, again, let's say t is equal to 1 nanosecond. The slope right here would be 1 over t, or if it was 1 nanosecond, the slope of this would be 10 to the 9th. If I asked you, I said, okay, well, so it takes 1 nanosecond for this guy to go from 0 to 1. The slope is 10 ninths. If I asked you to sketch the derivative versus time, all right, let's think about that. So before t equal to 0, this function's equal to 0. What's the derivative of 0? 0, right? This guy's going to be flat. And then let's do it after time t, where he's constant again. So here's time t. What would the derivative look like from t to infinity? So I'm taking the derivative of 1. What's the derivative of 1? If I have a constant number 1, 0. Right? So this guy's going to be 0. Now, between 0 and 1 nanosecond, what's the slope? What's the derivative? The derivative is the slope of that line. How would I express that from 0 to t? How would you sketch that?
1 over t.
1 over t, yeah, it's a constant, right? And this guy would look like this. So he'd be really high, and then he'd go back to 0 again. Okay? So this height here would be 1 over t, which if this was 1 nanosecond, this would be 10 to the 9th. Okay? So if we're talking like, I had an inductor and the current was changing, that implies that I get 10 to the 9th volts or something like that exists for some short period of time. And that happens, okay? In real world situations. I get spikes that are that big. But what happens is I try to shrink this down, right? As I make this smaller, what's going to happen to the height of this thing? It's going to go up. And in theory, if I can get t all the way to 0, if I can shrink this guy all the way down to here, what height would this reach? Yeah, it would reach infinite. Right. So what we say is that, yeah, if you think about, in calculus, they kind of shy away from this. What we tend to do is we say, well, in a more generalized sense, I think of the derivative at that point as simply being delta of t, right, is what I say. So in other words, I often, and this is what I say is if I think about taking the integral of the function up here, or taking the derivative of the function at the top, the derivative looks like this. So if I take the integral of delta of t, it becomes equal to 1. All right. So that's the relationship, the basic relationship that we have, right? The impulse function, kind of cutting it off there at the beginning, the impulse function delta of t is the derivative of the step function. All right, is basically the way we think of it. All right. And that ends up being useful in things that you guys will do in signals and systems. All right, so let's say I was asked to sketch the derivative of this function. So f of t is that guy up top. I want to figure out f prime of t, the derivative. I know this is the most boring thing in the world here, right? I get that. But we need to understand it at least, right? What would this look like? What would this derivative look like? So from time t equals 0 to t equal 1, what's the function from 0 to 1? Well, it's linear. So if I said sketch the derivative of a linear function, what would I get? So if I'm going up like this, what's the derivative look like? It's constant, yeah. This guy would actually be equal to 1 if I calculated the slope. And then it's actually equal to 1 again from 1 to 2. It's actually equal to 1 again from 2 to 3, which means it should be constant like this. All right, so 2. Now, what I didn't include is what happens at 1 and 2. Well, what you guys would have said in calculus is you would have said, well, it's undefined at t equal to 1, undefined at t equal to 2, right? In this case, if I take a jump from 1 to 2, I'll say this guy is actually a delta function right there, right? And I wouldn't say delta of t, but I've actually moved that guy over by 1. So if I have a shift like that, if I took the delta of t, which is defined at t equals 0, and I shifted it over, how would I write that? Delta of t minus 1. What about here? So I actually go up here, and then here I go down, and I went down by 2. What do you think I do there? Negative 2t minus 2, right? Because this guy actually, so we're going to talk about the value of this in a second, the number that I put in front of here. The first thing is I should see that I moved the delta over by 2 seconds, all right? That's why I get the t minus 2. Let's talk about the amplitude. Let's talk about the number out front, all right? So oftentimes what we do is we often label these impulses with their area, okay? So in this particular case, what I've written out is I've got this guy here, so I've got delta of t, and then I have this other function that's defined at t equal to 1. This function x of t is given by this expression here. So delta of t is this impulse. 2 delta t minus 1 is this guy right here. Right, so let's think about this for a second. What's the t minus 1 telling me? Shift to the right, okay, by 1. What's the 2 telling me? It's not telling me the height. What it's saying is that this guy has twice the area of that. Right? It doesn't really make a whole lot of sense to talk about the height being bigger because we said this guy is really thin and effectively infinitely high. What's that mean for this guy? He's 2 times infinitely high, right? That's where we get into the fact that these things don't really mean a whole lot when we're talking about infinities, right? However, the area here is twice the area there, right? And it kind of makes some sense. If oftentimes you really want to rationalize this stuff. The way I do it is if I look carefully at the fact that this guy, there's no way he could effectively go from 1 to 2 in 0 time. there would have to be a little bit of change to it. If you thought about that, you would actually see that this change here would effectively have twice, this change here would effectively have twice the height of that one. Okay, if you thought through that. But we typically think of these things in terms of areas. And so I say if I have A times delta t, so I have a number in front of it, and I integrate from negative infinity to positive infinity, the value of this is A, whatever that number is, right? So basically an impulse A times delta t, we say has an area A, all right? All right, so there's a lot of things that we can kind of say about this guy. Sometimes we refer to this thing and we talk about what we call the sifting property, because we often basically use the situation where we take another function. In this case, I'm saying I take a function f of t, multiply it by delta of t. What we say that it does is it sifts out the value of that function. It basically pulls out the value of that function at that time, right? That the impulse is applied, right? So if I have this function here, f of t, and I multiplied f of t by the impulse, right? So I took f of t and multiplied it by the impulse. So let's say f of t looked like this. And so f of t was just some function here. If I took delta of t and multiplied it by f of t, what that does is it pulls out the value of that function at only f of 0, right? At where the impulse exists. It's a weird concept, but we use it a lot. One place where we use it, like, so for instance, in your project, I gave you audio waveforms that were digital waveforms that had been sampled, right? We think of the sampling process as basically being, we model it as basically multiplying a series of impulses by the original continuous time function. And we think of that's a way to model the process of actually sampling a signal. All right, so we use it a lot. You guys are going to use it a lot more in later classes, but you got to understand the basic concept here. All right, so basically what it's saying is, let's say I have this right here, and I have some function f of t, and I have that waveform right here. All right. So just to make sure that you guys understand the concept of shifting, right? So here I'm saying this impulse exists at t equal to 2. If it's at t equal to 2, how do I write this in terms of delta? Yeah, t minus 2. Like that. Okay, so I would say f of t is equal to delta of t minus 2. And you can always check that by saying, well, what happens if I put in t equal to 2? Well, this becomes delta of 0, right? So that it should make sense what I'm doing when I go through that process. All right, so let's talk about this function that I have here. All right, basically what I got is a periodic function. We're going to talk a lot about periodic functions later, right? A periodic function repeats with some periodicity. All right, and so if I look at this guy, and I'm going to ask you in a second, what's the period of this thing? Because I want to, you guys, we talk about periods in terms of sine waves, but this guy is also periodic. So we should be able to define its period. Let's talk about how we would write this function. I have a series of impulses that keeps repeating, okay? The height of each of these impulses, or sorry, the area of each of these impulses is 1, all right? And they're all kind of shifted. So the first one here is pointing up. It has an area of 1 at time t equal to 0. Then this guy has an area negative 1 at t equal to 1. This guy has an area of 1 at t equal to 2. So how would I write this function?
Minus 1 or 10. Right.
Well, so it's a series of added impulses, right? So well, first of all, if I had this guy right here by himself, right? If I had him by himself, I would say that that's delta of t. And delta of t is equal to basically saying, you know, it gives me an impulse at t equal to 0 and it's 0 everywhere else. Okay. So this guy here, I would add on to this. What would I put for that? Negative, yeah, it'd be negative 1. So I'd say negative 1 times delta of what? T minus 1. Because I basically took the impulse, shifted it to the right one, and then multiplied it by negative 1 to flip it over. What would I say here at t equal to 2? Yeah, plus delta of what? Negative t minus 2, yeah. And then at 3, so here's t equal to 3. Negative delta of t minus 3. And then it would continue like this. Now, one thing that we're going to talk about a lot more as we get into Fourier stuff is how would I define the period of this thing? This guy is periodic, right? You guys think of the period as if I give you cosine omega t, you say omega is 2 pi over t. But the definition we gave is we said, all right, if I have a function x of t, where does it repeat? Right? Capital T, the period, is the time that it takes for the function to repeat itself. So in this particular case, how long does it take for the function to repeat itself? Not 1. 2 seconds, right? Because the value here and the value at t equal to 2 is the same. All right, we're going to deal with that more because we're going to get into more generalized periodic functions. This guy can be viewed as a sum of sine waves. I can figure out what are the amplitudes and phases of a bunch of sine waves that add up to make that thing. All right, and that's the kind of thing that you're going to do later on in the next couple of homeworks. All right, but so we'll deal with this question of the periodicity a little bit more later. All right, but this idea of the sifting property that we have, okay, we're gonna deal with that concept a lot, or not a lot, but it's important to know. There'll be a couple of problems on the homework about it. If I look at this here, all right, I have this function f of t, right? It's just going along. I didn't give you a formula for it. It's just f of t looks like that. Over here, this guy is delta of t plus 3. Why did I say delta of t plus 3 for this? Because it's shifted over here to the left, right? At t equal to 3. Right. So if I look at what is the value of this function, so if I multiply this guy by that, and then I took the integral from negative infinity to infinity, what would that be equal to? Well, the whole idea of this sifting property is he basically just takes out for me the value of the function at wherever the impulse exists. So if the impulse exists at t equal to negative 3, this guy sifts out, quote unquote, removes the value of the function at that one point, right? So this is a way that, and again, if you think about the way I sample things with an analog to digital converter, this really kind of models what an analog to digital converter does. It pulls one value off of that function, stores it in memory, and then I do it again and again and again, all right? So that's one of the areas where this thing becomes really useful. All right, so let's say I have this, all right? I have this function x of t, which is a bunch of impulses. And then I have this function f of t, and I multiply x of t by f, and then I take the integral from negative 2 to 3. Okay. So let's start out. Let's figure out what is x of t, first of all. What is the function that I've written here? So I got a bunch of impulses. Let's go from left to right. There's 3 impulses. Going from left to right, what do I have? How would I express this guy that's located at -1? Delta of t plus 1, because I shifted that to the right, sorry, to the left by 1. Right? Then I have this guy has got a negative area of 3 at t equal to 1. So what would I do with that? Negative 3 delta of t minus 1. And then what do I do here? Plus 2 delta of t minus 3. Like that. All right, and then f of t is whatever goofy function I just kind of sketched out down there. All right, I don't really care so much about what the function looks like. I want to think about what's the sifting property do here. So if I'm going to plug that in here and say, okay, well, the integral I wanted to calculate is from negative 2 to 3 of f of t times x of t. And x of t, I just figured out, was this delta of t plus 1 minus 3 times delta of t minus 1 plus 2 times delta of t minus 3, all times dt. Okay. All right. What's the idea of the sifting property? Well, it pulls out the values of that function at the times where the impulses exist. So at what points would it pull values off of functions, f of t? At what t values would I pull values off of function f of t? At -1, so I'd pull off the value where this guy exists, right? I'd pull off the value where this guy exists at 1. And then I'd pull off the value at this point. Okay, with one exception. All right, so let's go through this, right? So let's think about this for a second. So at t equal -1, what value would I pull off? I pull out f of -1. So I'm going to say I get f of -1. What happens here at this point? What would I pull off of here? Well, I pull off the value of f of t at t equal to 1. But what do I multiply it by? -3. So it becomes -3 times f of 1. What about at t equal to 3? What should it be? What about at t equal to 3? Just to be clear, here what I did was because that's the summation, I can break that up into 3 integrals like that. It's probably easier for you guys to look at it. So what I did here is I said this guy becomes 3 integrals. This one, and this one. All right. The first integral is f of -1. The second integral is -3 times f of 1. What about this last one? +2 times f of 3. That's exactly what it looks like it should. The catch to this one is what? Catch on this. This is where I have that ambiguity of the limits. Right. It's undefined because that t equal to 3 is right at the limit of the integral. It's unclear. And we say this guy is actually 0. Right. 2 times f of 3 is what it looks like it should be. But this particular case, because that limit is at t equal to 3, it's not officially enclosing it. That's sort of the ambiguity of the way this thing is defined, because we don't say it's defined to exist at that point. It's an area that basically exists from a little bit before to a little bit after. All right. Now, if the limits were different, if I was saying I was integrating from -2 to 4, right, then it would have been fine. All right. But because I said I'm only integrating up to 3, it doesn't count.
So if it's included or not is defined by a positive or negative sign in front of it, right? Or is it after?
Well, so sure, if I had said that it was going to like that, like 3+, that would say it was included, right? Because a little bit after, yeah.
You would add another negative factor. Like if -2 was included.
So yeah, if -2 was included, it would have to start a little bit to the left of it. So it would be -2 minus or something like that. Yeah. So I mean I would probably say like -1.9999999, then it would be included. Right. If it was -2, no. Or sorry, it would -2.0000021. So that's the way. Okay. All right. It's really fairly easy to do those problems. All right. So it's not too particularly bad. All right. So you'll get a couple of problems like this stuff on the homework. The majority of what you're going to be doing is going to be related to our next concept, which is the Fourier series, which I want to kind of introduce a little bit in the time I've got left today. And we're going to do plenty more of this over the course of Thursday and all of next week. So I want to go back to a concept that I know was something we did a little bit in the first part of the class on the first exam, but how I kind of related cosine and sine back to the complex numbers, right? So I want to sort of frame up this idea. This is a very common waveform that we get in circuits here. This is a square wave, right? Square wave happens all the time. All right, I'm going to give you a couple of examples, but one area where you know it exists is in digital circuits. You have clock waveforms, right? A clock waveform basically goes from low to high and then back to low and then back to high, and it's periodic. Okay. I can have a voltage source. You guys can go into the lab this afternoon and you can make your function generator generate that waveform. Mathematically, what you have created basically is that voltage source, right? You can model your function generator as a voltage source that looks like this, right? Looking into these terminals, I get a voltage that has that property. How do I write that guy mathematically? It's hard, all right? It's hard to write I can draw it easily. I could think of this in terms of a bunch of unit steps, like a unit step up and then one down and then another one up and another one down. Very hard to write it. In reality, any kind of periodic waveform that I have can be written as a linear combination of what I call periodic basis function. In other words, I can take some amount of cosine and some amount of cosine 2 omega t and some amount of cosine 3 omega t and add them up to create that. So let's stop for a second. When we talk about Fourier, this is the concept of Fourier. Any periodic waveform is made up of a sum of sine waves. And I want to introduce a quick concept here real quick. So I said it takes some amount of cosine, some amount of cosine 2 omega t, some amount of cosine 3 omega t, and we add them together. Now, a lot of what we're going to spend our time on is this notion of how much is some amount of. In other words, what amplitude do I choose for this guy? And what amplitude do I choose for that guy? All right. And what amplitude do I choose for this one? But notice what I'm doing. I'm not arbitrarily doing. I'm saying that some amount of cosine omega t, some amount of cosine 2 omega t, 3 omega t, 4 omega t, 5 omega t. I didn't say cosine 1.5 omega t, right? I'm basically choosing integer multiples of some base frequency that we call a quote unquote fundamental frequency. All right. So the terms that I use here for omega, 2 omega, 3 omega, 4 omega, so on and so forth. You guys have maybe heard the term for those, but how do I say those are related? What do I call those? Anybody know? I say they're harmonically related. All right. So, and you kind of know this. This gets into music, and music I can talk about harmonics. You might have heard that term before, but basically, if I have a set of tones, right, a set of sine waves whose frequencies are integer multiples of each other, those are what we call harmonics. Right. So these signals are harmonically related. And we're going to talk more about how we figure those values out. But I wanted to introduce the basic concept at least. Now here's a place where I often use that. All right, this would be, again, where would I apply any of this? So this would be if I have a solar panel, so I say PV panel, right, photovoltaic panel. This would be if I had a single panel. All right, that's a DC output. All right, this PV panel, if it's a single panel, I don't know, this might be about 30 volts or thereabouts. And I might have, I don't know, on the order of 10 amps or something flowing out of this thing in the middle of the afternoon, right? That's pretty typical for what I might see on a solar panel. Now, this box I drew right here is something you're going to deal with in the second project. It's an inverter. What it does is it goes from DC to AC. All right, so this guy here is an inverter. And if I look at this output of this inverter, V sub I looks like that. All right. Looks like a squarish waveform that goes high, low, high, low, high, low, high, low. All right, real ugly looking. It is nothing like the voltage over here on the grid. Just to be clear, what am I doing? So I'm going from a PV panel, which is DC. Then it goes over to the grid. What's the grid voltage? Well, it's a sine wave. What's the frequency that it's supposed to be? 60 hertz. All right. And the amplitude of it depends on where I'm connecting to it. All right. For this guy here, this would be of a single panel, probably would be something I would have on a rooftop of a house. The amplitude here would be 240 volts, probably, if I'm looking at a single thing on a house. All right. The amplitude doesn't matter too much to me. What I have is this V sub I comes out of this thing. And I got a filter. I had this LC and another L, hopefully making a current that I called, all right, the current that I'm measuring here, calling it IG, G for grid. I want that to look like a sine wave, right? So what's happening is I can think of the output of that V sub I, that the inverter output, looks like this. And it's basically, if I look at this carefully, it's hard to figure out what frequency it has because it's so ugly looking. But essentially what it is it's a periodic waveform. And any periodic waveform can be thought of as having basically a set of harmonically related sine waves. What this filter does, what this L, C, and L does, is it basically removes all the high frequencies and leaves only the 60 hertz behind. All right, that's the magic of how this thing works. So in order to design a system like this, if I want to design how this guy's going to operate, I need to understand the concepts of Fourier series to be able to ever do it. All right. So as an example of where we might use this, I said the voltage that I measure on the grid should be a 60 hertz sine wave. Okay, should be. This guy is the voltage that was measured in a lab here in EPIC. All right, in the EPIC building. Now, we scaled it down. It's only 60 volts peak. In reality, it's bigger than that. All right, so I scaled the amplitude down, and you have to a little bit to measure it. This guy is a frequency of 60 hertz. The way I can see it's a frequency of 60 hertz is right here. 0.0167 seconds is how long it takes for it to repeat. If you look at that carefully, 1 over that's the frequency. 1 over 0.0167 is about 60 hertz. Okay. Does that look like a sine wave? It probably looks like a sine wave that I might draw by hand, but it looks like crap, right? But it actually has structure to it. Not only does it look like something, I mean, if I drew it by hand, it would be unstructured. It would be off in all kinds of ways. This guy's actually kind of repeating himself. He's got a unique ugliness at the zero crossings and a unique ugliness at the tops. Right? A sine wave should be rounder and it should come through zero pretty much linearly. And this guy is all kinds of off. This guy has within it a bunch of harmonics. And if I looked at this carefully, what I would find is he's got a lot of 60 hertz. He actually has a fair amount of third harmonic, which is 180 hertz. A bunch of fifth, a bunch of seventh, which would be what? 420. Right? He has a bunch of those frequencies. It doesn't have any, turns out he doesn't really have any of the even. So 120 hertz would be 2 times 60. Right? Doesn't have much 4 times 60. Doesn't have much 6 times 60, but he has a lot of those things. It actually has a lot of the 300 and a lot of the 420. Right? So one of the things that we often do, and again, the example, we use this a lot in power. So in that inverter that I was showing there, when I first run this inverter, that waveform probably doesn't look as clean as it is. All right. So here's the situation. So here's a voltage. This is actually a current, that dashed waveform there. What I'm showing here is basically this guy. Anybody know what this is? So I'm basically showing at each harmonic, I'm showing what percentage of that waveform that I have at that particular harmonic. Anybody know what that is? Some of you actually used it and showed it to me on the project. Whether you realize it. So that's an FFT. That's a Fourier transform. What this thing is telling me, So we're going to learn a little bit about the Fourier transform. First thing I'm talking about is the Fourier series, which is the basic concept, right? And then I take it to the Fourier transform. Fourier transform basically tells me at what frequencies do I have information in that signal and how much, right? So the height of those things tells me kind of how much information. So what this tells me is that for the ugly waveform, the dash waveform right there, I have a lot of third harmonic, right? A lot of the 3 times the frequency. Oh, right. I have a lot of the 3 times the frequency. I have a lot of the 5 times the frequency. I have a lot of the 7, not as much of the 9. Right? Now, for the prettier looking waveform, in other words, I say it's prettier. Why do I say it's prettier? That's a very objective term, right? Prettier because it looks more like a sine. That's what I mean by that. Right? So it's not purely a sine. I can see, you probably can't see it as well, but I can see that it's not perfect. It should be rounder up at the top. But basically, if I looked at the prettier looking one, that's how much third harmonic it has. And here, and here, and here, and here, and here. So much, much less. So it's much closer to what it should be. This is a concept we use a lot. This guy is basically using what I call a power analyzer. Right? So he's analyzing the waveform, telling me how close he is to what's ideal. If I get into a situation where I have voltages on the grid that look like that, customers are going to be complaining left and right because their equipment's going to fry and bad things are going to happen to their equipment. All right. So the utility has a responsibility to provide waveforms that look pretty, if you will. They have to have what I call a high degree of power quality. So it's a concept that we use often. All right. So all that said, in order to be able to think about any of this stuff in a mathematical sense, I have to go back to sort of the multiple ways that we've learned of thinking of the sinusoid, the sine wave. All right. And we basically know 4 different ways at this point. All right. In general, if I have a sine wave, we said we think of it as some waveform with an amplitude, a frequency, and a phase shift. Like that. Okay. That's our basic way of defining it. That waveform can be thought of in 3 equivalent ways. The first equivalent way is to say, I can think of this as basically an additive combination of a sine and a cosine. Okay. I can also think of it using 2 vectors that rotate in the complex plane. All right. What gave us this thing here? Back on exam 1. Euler's identity, right? Euler's identity gave us this thing. All right. And we're going to do an example here in a second, but you kind of know this. What I do is I call this coefficient right here CE to the J phi over 2. That's this, I write it as this coefficient alpha. And I write this guy here as the coefficient alpha minus. Now, if I looked at these numbers here, in this particular case, the value of C is a real number. Okay. So if I think about this, this gets you guys confused. But if I tell you I have C over 2 e to the J phi n, and that's equal to alpha 1. That guy is a complex number. And he has a magnitude and a phase. You guys don't like it when we write it in a complex exponential form. If I wrote that in polar form, right? How would I write this in polar form? C over 2 is the magnitude. And the angle phi n is its angle. Okay. Looking at this then, how can I express this guy? C e to the negative J phi n over 2. How does that relate to this guy? It's the what of it? It's the conjugate of it, right? So I can see that alpha minus 1 is the conjugate of alpha 1. Now, the other thing we learned too is this guy here, and you use this all the time in circuits too, right? Is to say that this guy up here can be thought of in terms of the real part of some dynamic phasor the part that you use in circuits that I called the static phasor. In circuits, all right, unfortunately in this class, I'm bound by more strict mathematics. So C e to the j phi n, right, I say is the static phasor. In circuits 2, you would call this C angle phi n, and you'd be all happy about it. You'd be happier, at least, right? It looks ugly when I say it's the real part of that, right? But this concept, all 4 of those waveforms are the same, right? And we need to be able to go back and forth. But why do we need to go back and forth? Because honestly, when you're in circuits, the most useful way to do the analysis is with this, right? And actually, the easiest way to do the analysis is really just with this, and to relate it back to the way it exists in the real world. In other words, in the real world, we don't have vectors that are rotating back and forth in the complex plane. If you look on an oscilloscope, you have a voltage that goes up and down and up and down and up and down. I think of on an oscilloscope in the real world, I have something that looks like the top waveform. Doing the analysis, doing the calculus that's required with Fourier series with that is ugly and hard and gross. All right. Doing the analysis with this approach is usually a heck of a lot simpler. Although you can do it with all 4 of these approaches. We typically use this third one. All right. So we're going to go back to remembering that analysis that we did in the first part of the class. All right. So I'll say I've got this guy here, C cosine omega t plus phi. I guess I wrote it out here, but for this guy, I see that phi is equal to 0. In this particular case, I've got phi equal to negative 90, and I basically shifted this guy over, right? So basically, it's equal to a sine kick. Let's think through something like this. Let's say I've got C cosine omega t plus phi. Somehow that is the combination of a cosine and a sine together. How can I figure out what that combination is? In other words, if I have C cosine omega t plus phi, to me, I look at this and what that says is it takes some amount of cosine. So the A tells me how much, and the B tells me how much of sine to equal this. How much of cosine do I have to put together, and how much of sine do I have to put together to equal that? Okay. And if I think about it, in this particular case, cosine exists like this. Sine is shifted by 90 degrees. So it's basically saying some amount of cosine and cosine shifted by 90 degrees added together equals the original waveform. How do I figure out how much cosine and sine to add? Well, I know a trig identity here that I can apply to this. So there's a trig identity. No one probably remembers what it is, but basically I'm saying if I had cosine of A plus B, there is a trig identity for that, which I can look up. Right? Any idea what it might be? So yeah, cosine A, cosine B, minus sine A, sine B. So if I applied that here, right, where this would be A, this would be B, this thing would become C cosine omega t cosine phi minus C times sine of omega t sine of phi. And I rearrange that a little bit to become C cosine phi cosine omega t minus C sine of phi sine omega t. Now what I do is I look at this and I say, all right, well, I want to match this to A cosine t plus B sine omega t. Right? So this looks like the A value, doesn't it? What's my B value? Yep. B is apparently negative C sine of phi. And A is C cosine of phi. All right, so let's look at an example here. All right, so there's x of t. X of t is 2 cosine 2 pi 1000 t plus 45 degrees. All right, and so what I've sketched here is basically x of t, that's the blue waveform. And then I've also sketched a cosine and a sine. All right, so let's check this for a second. We should be able to make some sense as to what I'm doing here. Which one is the cosine and which one is the sine? Let me check you on that part. Which one is the cosine term? Which one is the sine term? Here's t. I know it's cutting off the bottom here. This is t equal to 0. Which one, the yellow or the red? Which one is the cosine? Which one is the sine? The red is the cosine, right? And the yellow is the sine. Okay. All right. So according to this, right, previous slide, I said A equals the amplitude times the cosine of phi. Let's check this for a second. What's the amplitude of x of t? So x of t is 2 cosine 2 pi 1000 t plus 45 degrees. What's the amplitude of that? All right. If you don't know that, I really shouldn't send you to Signals and Systems. They're going to roast you in 3100. What's the amplitude of that? 2. Right? The amplitude of that is 2. All right. What's the frequency of it in hertz? 2 pi 1000 t. What's the frequency of that in hertz? 1000. All right. So, all right, c cosine, but this guy becomes 2. What's phi? What's the phase? 45 degrees. 2 cosine 45 degrees, which is what? Cosine of 45 works out to be 1 over square root of 2. So this becomes 2 over the square root of 2, or about 1.4. Okay. And let's see. So the amplitude here is right about here. So it's actually it's about 1.4. In reality, it's about 1.44, something like that, or 1.414. Right. That's about right. Okay. What about the B term? Well, I just said that that was minus c times cosine of phi. So what's that going to be? So the amplitude is 2. Sorry, sine of phi. What's the sine of 45 degrees? It's also 1 over square root of 2, right? So this guy becomes negative 2 over square root of 2. So it becomes approximately negative 1.4. How do I see the amplitude? So I see the amplitude is here. How do I see the negative? How can I tell it's negative?
It's starting going down.
It starts off going down. Sine's supposed to start out going up at t equals 0, right? So this guy's starting out going down. I can see him peaking at about negative 1.4. All right. That's about what we would expect. So when I add the two of those up, so when I take, so essentially 1.4 cosine omega t minus 1.4 sine omega t. When I add those up, it basically makes this blue graph. It should kind of make sense, right? Where does the maximum value happen? The maximum value happens, let's say, right here. Basically, where these two guys cross over, that's where they sort of additively interfere with each other. A term that you might have heard in physics, right? And I can potentially make them destructively interfere with each other, so they perfectly cancel each other. All right. And that would take a special value for phi and for the amplitude. Okay. Now the third way to think about it, which we're going to pick up more probably on Thursday, is to say, at least want to kind of start it here, is to say that I can think of using Euler's identity. All right, using Euler's identity. I can think of c cosine omega t plus phi n as 2 rotating vectors. All right, now, which of those, so these two vectors, we talked about this before, these vectors rotate at a particular rate. All right, which one of the vectors rotates in a positive direction? Is it this one or this one? Which one rotates in the positive or counterclockwise direction? Which one moves in the positive direction? Which is, yes, this one, right? This one moves in the positive direction, counterclockwise. That would be this one. The one that moves in the clockwise or negative direction is this guy. Now, I have plotted these in this particular picture at t equal to 0. And I'm saying that this angle from 0 to here is phi sub n, and the angle from here to here is negative phi sub n. All right. So we used that approach before. And let's say I've got this guy here. Again, same waveform. 2 cosine 2 pi 1000 t plus 45 degrees. And I'm saying that can be written as alpha 1 e to the j omega t. What's omega here? Two pi 1000 t, right? Times, right? So I'm saying alpha 1 times that plus alpha minus 1 times e to the negative j 2 pi 1000 t. My alpha 1, I said, is the amplitude divided by 2, and then whatever that angle is, phi sub n. Alpha minus 1 is its conjugate. Okay, so let's think about this. What should this be? What is c over 2? So what's the amplitude of 2 cosine 2 pi 1000 t plus 45? What's the amplitude of that? 2. But c over 2 is then what? 1. What's the angle of this thing? 45 degrees. So to keep it simple, let's just write it that way in polar notation. 1 angle, 45 degrees. Where do I sketch that? So this, I drew a circle here with a radius of 1, a circle here with a radius of 2. Where would I put alpha 1 in the complex plane? 1 angle, 45 degrees. Where does that go? He would be there, right? So his conjugate, what's the conjugate of 1 angle 45 degrees? The magnitude's still 1. What's the angle of it? Minus 45. So that guy would be where? Yeah. Like that. So this term here is that guy. This entire term here is this guy. I'm showing this at t equal to 0, but the two vectors would rotate. Right? The calculus with this becomes a lot easier. Why does I keep saying this term? The calculus with these, I recognize that this is a difficult concept to kind of jump from a cosine to these two complex exponentials. I get that. Weird, right? Because we're using imaginary numbers. Why do we do it? Just for the sake of doing it? Well, we do it because the calculus is a heck of a lot easier. Right? When I have calculus with exponentials, what's true about that all the time? Right? E to the AT. Doing calculus with e to the AT is simple, right? And it becomes a lot simpler than doing calculus on cosines like this, and sines like this, right? There's all kinds of negatives. So when I got to remember when to do negative signs, when not to, and all that kind of stuff. When does cosine become sine? This becomes a much simpler approach for doing the calculus. Very often with this stuff, you end up doing integration by parts if you have to do cosine and sine, whereas it gets a lot simpler when I have to do it with complex exponentials. And even nicer with the complex exponentials, it lends itself nicely to things like, I mentioned it very early in the semester, things like the FFT, where the math can be done really nicely and easily inside of a computer. All right, if we use that approach. All right, so I'll stop there. We'll do more on Thursday.